This is Iceland. Known around the world for its glaciers, black sand landscapes, and being a hotbed of volcanic and geothermal activity. But is Iceland more than this? Can Iceland show us the clues to the way the climate is changing all over the world? And are the people of Iceland finding unique ways to lessen the impact humans have on the planet?
With the consequences of global warming no longer an imminent threat, but a very present reality, government leaders and scientists alike are searching for solutions to try to combat climate change and reduce greenhouse gas emissions. But they need look no further than Iceland. Here we have not just an environmental success story, but an economic one. Throughout the 20th century, Iceland went through a huge period of transformation. Initially, it was one of the poorest countries in Europe, and it was dependent for energy upon peat and coal that had to be imported from overseas. But within the next 100 years, it had advanced to a country with a high standard of living, and it was nearly totally dependent on renewable resources. In 2014, 85% of Iceland's primary energy use was from renewable resources, and a huge 66% of this was from geothermal energy. Geothermal energy has only been around since 1904, when it was first produced in Italy, but it's Iceland who have really blazed the trail with this form of renewable energy ever since then. So what makes Iceland so ideal for geothermal energy, and how does it all work? Well, it's mainly down to its geologic location, right over a rift between two continental plates, and the mid-Atlantic ridge has formed an active volcano belt stretching from the southwest to the northeast corner of Iceland. And it's this volcanic belt which causes upwelling of magma, which has been responsible for the creation of 32 high-temperature geothermal fields. These fields are basically just underwater reservoirs. Sometimes they're 1,000 meters deep under the Earth's crust, and they can reach temperatures well in excess of 200 degrees Celsius. They create immense thermal energy, and this thermal energy, either in the form of hot water or steam, can be used to turn turbines, which then generates electricity. So I'm here at the Hellisheidi geothermal power plant, and I think that if I go through this door, I should be able to see some of the turbines that are driven to produce the electricity. So let's go and take a look. Wow, you can certainly hear it. This power plant is actually the largest geothermal power plant in Iceland, and it's still in the top 10 largest in the world. It generates a colossal 303 megawatts of energy, which is pretty impressive. But it's because of where this energy actually comes from. So Hellisheidi is located on the Hengil volcano, but it's not just one volcanic system, it's actually three which interlink together, so we've got triple the energy going on. You wouldn't believe it to see it, but it only became operational as a power plant in 2006. Since then, they've done two really big stages of expansion, and they're looking now, this is what they're working on right here, not just to produce electricity, but to produce hot water as well. However, there are huge downsides to geothermal energy production. The company can lose a great deal of money if the geothermal energy which they're working in cools down, or if they inject too much water into the rocks, meaning that area is no longer effective at producing high temperature geothermal energy. In addition, although geothermal energy works really well out here in Iceland, it can only ever be used in areas where there are tectonic activity like this. You can't easily transport geothermal energy in the same way that we can transport fossil fuels, such as coal. This means that although it might provide a small-scale solution to the problem of climate change, will it ever be applicable worldwide?
While geothermal energy is a fantastic thing for Iceland, provides virtually free energy out of the heat of the earth, it's not all good news. When you start digging up all of that gas and actually, in this case, pumping it as water upwards, you actually bring with you a lot of other things. There's CO2, there's hydrogen sulfide, which is that stuff that really smells of bad eggs. It also brings up very trace minerals of things in the water itself, so arsenic and mercury amongst other things. Now those can be dealt with, they're pumped back underground with the rest of the water, but the CO2 and the hydrogen sulfide, they're both an issue because those are both greenhouse gases which need to be dealt with in one way. And what happened here at Hellas Heidi is something very, very interesting. Normal carbon capture and storage works using a chemical called an amine, and the carbon dioxide is bubbled through this liquid chemical and eventually can be stored again as a gas, but separated from everything else. What that means then is that you have to store that gas somewhere, and that's not a great idea because that gas can sometimes escape. What scientists have done here that is so pioneering is that they've actually pumped the gas underground, and the idea is that over time it will slowly get remineralized, in other words, turned into a rock itself. And that's a much safer and more secure way of storing carbon. The key to this experiment was the ground upon which this Hellas Heidi plant lies. Because it's a volcanic region, a lot of this rock is basalt. And that's actually perfect for this experiment because basalt rocks contain the right minerals to turn the CO2 back into rock again. Crunch time came 2 years later when the scientists had to dig up what they'd buried. They used big drilling equipment to bring out cores of rock, and when they looked at them, they found that not only some, but nearly all of the CO2 had been absorbed, had been remineralized. This has big implications elsewhere because they were just testing this here with 230 tons of CO2. The whole world produces thousands of millions of tons of CO2 each year. So technology like this could help us to find a way of dealing with that CO2 and mitigating the effects of climate change.
Every 3 to 7 minutes, something pretty spectacular happens here, which is absolutely impossible to ignore. That was Strokka, a geyser, which is basically just a geothermal fountain. And as you just saw, it's capable of shooting jets of water up to 30 meters into the air. Strokka wasn't really discovered until 1789, when it's thought that an earthquake opened up a crack which allowed the water to force itself through in quite a dramatic fashion.
When you think of Iceland, tomatoes might not be the first thing that comes to mind, but here we are in a greenhouse full of them. And the reason they're able to grow tomatoes here at Fríðheimar Farm is because they take advantage of a nearby geyser. And the water comes out of that geyser at 95 degrees Celsius. And it then travels through these pipes here into the greenhouse. And you can see with our heat sensitive camera that they're at about 50 degrees Celsius. And that keeps the greenhouse above 20 degrees Celsius so the tomatoes can grow happily. But also, if you look up, you can see that we've got some high pressure sodium lights, and they provide the tomatoes with some artificial sunlight. They're on for 17 hours during the winter, but a mere 14 during the summer. So the next time you think of Iceland, think of it as the land of ice, volcanoes, and tomatoes.
runs the river Skua, and whilst the waterfall is impressive in itself, one of the most amazing parts about this waterfall is that this used to be an old coastline for Iceland, but now the actual coastline for Iceland is 5 kilometers that way. It's one of Iceland's biggest waterfalls at 25 meters in width and then over 60 meters in height. And further up the river, it's actually 20 more waterfalls. The waterfall is named after the town in which it runs through, which is Skua, and also the Icelandic for waterfall, which is foss. These places really give you a sense of how awesome nature is, but also how much it changes across the millennium.
When it comes to what icebergs can tell us about climate change, you might think that it's as simple as more global warming equals more icebergs, as they can melt away from their parent glacier. However, icebergs like these here can tell us so much more about climate change. They're mostly used to study what's known as ice shelf carving. Now, ice shelves are permanent floating sheets of ice that connect to landmass, and they can mostly be found hugging the shores of the Antarctica, but they can also be found in Greenland and in the Russian Arctic. Now, by studying the effect that climate change has on the melting of these ice shelves, we can look at how that influences glacial acceleration and that all-important sea level rise. Now, these ice shelves are disintegrating all of the time, but the complete process takes months or even years. What icebergs do is they give us an opportunity to investigate a similar process, but that happens over a shorter time frame. And mostly, scientists are trying to discover how this disintegration occurs. So whether it's due to surface pond melting or melting that happens right down at the base of the iceberg. And that's not all when it comes to studying icebergs and climate change. Research has revealed that the nutrient-rich plumes that icebergs leave in their wake when they melt can lead to the capture of millions of tons of carbon every year. And they do this because the tiny algae that are in these plumes absorb the carbon when they're alive, and then when they, or the many creatures that eat them, die, they sink to the bottom of the ocean, taking the carbon with them. So although global warming does obviously lead to iceberg melting, on the flip side, iceberg melting is doing its own part to counteract global warming.
This is the Solheimerjökull glacier. It's an outlet glacier that runs from the Mördalsjökull ice cap. It's about 14 kilometers long, 1 to 2 kilometers wide, and it descends about 1,000 meters from the frozen ice cap to the warm, humid lowlands. It's like a large tongue of ice sticking out towards the south coast of Iceland. The shape and location of the Solheimerjökull glacier make it particularly sensitive to climate change. Studying the sediments and landforms of the area allows scientists to build up a picture of the glacial history. Over the centuries, this glacier has advanced and receded, but it's now shrinking much faster than average.
We've just come across this sign pointing out that in 2010, the snout of the glacier came all the way to where we're standing now. That's a pretty drastic difference in not that much time. And actually the Solheim is one of the fastest retreating glaciers in Iceland. So we only really know the story of this glacier since around the 1930s. Since then, it's had a massive period of growth, quite a long way back. But now we're in a period of really quite rapid shrinkage. You can even see where the glacier used to sit out in the valley, where it has this really sudden change of gradient and the walls become a lot steeper and the rock looks a lot fresher. That's where this massive chunk of ice used to be barging its way down this valley, taking the sides with it as it went.
Iceland is one of the fastest warming places on the planet. Its 300+ glaciers are losing an average of 11 billion tons of ice a year. If this warming continues, in 100 to 200 years, the glaciers will have virtually disappeared.
The highest uplift rates that we measure now are about 4.5 centimeters per year. So this is at the places that are more or less within the Vatnajökull ice caps, measured at mountains that stick out of the ice caps. But outside the ice caps, we still measure about 3 centimeters per year. So when the ice melts, it affects the volcanoes in a few different ways. On the deep scales, when we relieve pressure, essentially, by unloading the weight of the glaciers, we change the melting conditions of the mantle from where we derive all the material for the volcanoes. So when we melt the ice, we are also melting more rocks or creating more magma for the volcanoes. And on the shallow scales, changes in the pressure from the ice can also affect the shallow magma chambers which are storing the magma and affect how likely or unlikely it is that they will erupt. About 12,000 years ago, Iceland was entirely covered with a glacier that was 1 to 2 kilometers thick. And this glacier melted quite abruptly about 12,000 years ago to something similar to what we have currently. And when that happened, we saw a huge surge in volcanic activity.
Anyone looking around at the surface of Iceland can tell that this is not exactly a stable environment. But what might not be quite so obvious is that while you're standing on this place, it's actually rising underneath your feet. Scientists have actually placed 62 GPS stations to monitor how the island is changing. And what they found is that in some places, it's rising by as much as 30 millimeters every year. Now, with Iceland being so geologically active, you'd expect that that's got something to do with what's going on here. But actually the major effect is climate change. Iceland is 10% covered in glaciers and ice caps. And they're now starting to warm, reducing all of that weight on Iceland. So this is a bit what happens when you remove the weight from anything. It's going to bounce back up again. And Iceland is bouncing back up at an ever-increasing rate. The latest study says that it might be coming up by as much as 1 or 2 millimeters extra year on year. And that means we're going to have to start watching out for what's going on around here because the effects of this are still quite unknown.
The land of fire and ice, an ever-changing landscape created by the extreme forces of nature. Looking back at the history of Iceland can teach us a lot about how the world around us was created, and watching it closely in the present could give us a good indication of what's going to happen